Raise a grain of sand to arm's length. That sliver of sky conceals 10,000 galaxies. Every galaxy harbors billions of stars. The whole sky holds 13 million such grains. James Webb just looked further. Across a field 3 times the width of a full moon, it cataloged nearly 800,000 galaxies. And it is now detecting galaxies that existed just 280 million years after the Big Bang. Already vast and fully formed at a time when the cosmos should have been little more than a newborn. Today, we watch galaxy clusters come into being, chart the unseen scaffolding of the universe, and confront a cosmos 2 trillion galaxies wide. If this stirs something in you, subscribe. Brace yourselves. We begin. The James Webb Space Telescope had been circling in orbit for precisely 6 months, when scientists directed it toward a region of sky they had visited many times before. The target was a galaxy cluster designated SMACS 0723, positioned approximately 4 billion light-years from Earth. It was a thoroughly catalogued cluster. Nothing about it was especially puzzling. A tightly bound collection of galaxies held together by gravity. The research team did not select it for what it was. They selected it for what it could accomplish. A single 12.5-hour exposure produced something that brought the room to a standstill. When the image materialized on monitors at the Space Telescope Science Institute on July 12, 2022, the scientists were confronted with thousands of galaxies packed into a patch of sky smaller than a grain of sand raised to arm's length. Not just the cluster itself, but galaxies lying behind it, billions of light-years deeper into the cosmos. Some of those background galaxies had been warped and smeared into glowing arcs by the gravitational pull of the foreground cluster, a phenomenon known as gravitational lensing that Einstein had predicted more than a century before anyone photographed it. The cluster had curved the light from those distant galaxies, the way a glass lens curves light on a tabletop, magnifying it, drawing faint objects into visibility that would otherwise be entirely beyond the reach of any telescope ever constructed. That 4 billion light-year mass of galaxies had transformed itself into a natural magnifying glass. And through it, Webb could peer into the early universe with a depth of infrared precision no instrument had ever matched. Scientists who had worked for decades toward that moment described the experience of standing in that room as a kind of vertigo. The image held galaxies at every scale, from relatively close objects displaying clear spiral structure to tiny ancient smears at the very boundary of what light has had time to deliver to us. Some of those smears originated when the universe was younger than 1 billion years. A handful seemed to reach back even further. The administrator of the National Aeronautics and Space Administration, Bill Nelson, shared the image with the President of the United States before it was released publicly. He called it the most profound view of the universe ever recorded. He was right at that moment. What the image demonstrated was not simply that the telescope worked as intended. It showed that Webb was performing far above its baseline requirements, capturing light with a precision and sensitivity that surpassed even the most ambitious engineering forecasts. Researchers had expected a machine that would press against the limits of the observable universe. What arrived seemed to occupy an entirely different tier. Yet, for all the weight of that first image, it encompassed only a fraction of what teams had spent years designing. Researchers around the world had devoted much of a decade to debating observing schedules, negotiating access, and charting which corners of the sky were most deserving of the most costly scientific instrument ever sent into space. The first deep field was, in a sense, only the opening beats of a far longer performance. Scientists already understood that the real discoveries would come once the telescope moved past a single cluster examined for half a day and turned toward broader stretches of sky observed across weeks. The figures extracted from those larger surveys would force a confrontation with everything cosmologists believed they knew about how galaxies are assembled, and the magnitude of that confrontation would prove unlike anything the discipline had anticipated. The story of how humanity began to comprehend the true scale of a galaxy-saturated universe begins with a decision that seemed, at the time, almost reckless. In December 1995, astronomers aimed the Hubble Space Telescope at a patch of sky in the constellation Ursa Major containing no bright stars, no catalogued galaxies, no known objects of any kind. Just a featureless rectangle of darkness. They held it there for 10 consecutive days. What that observation returned changed science's understanding of the cosmos fundamentally. Within that sliver of sky, so tiny you could blot it out entirely by raising a single grain of sand to arm's length, researchers counted approximately 3,000 galaxies. Each of those galaxies contained hundreds of billions of stars. Everyone had been sitting there all along, in a direction everyone had assumed was empty. The original Hubble Deep Field covered roughly 1/1,000,000th of the full sky. Scientists repeated the observation with greater sensitivity in subsequent years in a program called the Hubble Ultra Deep Field, and the count in that tiny window climbed to approximately 10,000 galaxies. 10,000 separate island universes, each comparable in breadth to our own Milky Way, all compressed into a patch of sky the size of a 1 millimeter square held at arm's length. Then came the arithmetic that genuinely unsettled people. The entire sky holds room for about 13 million patches that size. If each one contains around 10,000 galaxies, a rough extrapolation pushes the total galaxy count somewhere between 100 billion and 200 billion. That figure occupied astronomy textbooks for roughly 2 decades. It felt beyond imagining. It was also, as subsequent work would demonstrate, a dramatic underestimate. The point of the grain of sand exercise is not the final number. The point is the feeling that arrives when you hold that grain between your fingers and understand what it obscures. In every direction you can look, in every scrap of sky you can imagine, galaxies extend behind galaxies for billions of light years. The darkness is not vacant. The darkness is filled, and most of what fills it remains undetectable by any instrument humanity has ever assembled. James Webb was designed specifically to see what Hubble could not. The telescope operates chiefly in infrared wavelengths, allowing it to cut through the dust and cosmic redshift that renders the oldest galaxies invisible to instruments calibrated for visible light. Engineers understood before launch that a deep field observation with Webb would reach further back in time and further down in brightness than anything previously attempted. What they failed to anticipate was how quickly those observations would overturn every prediction. The Hubble Deep Field required 10 days to reveal 10,000 galaxies. The first Webb Deep Field image, a single 12.5-hour exposure, contained thousands of galaxies and structures the Hubble era had never hinted at. And Webb was only beginning. Astronomers had already drawn plans for something on an entirely different scale. A survey that would cover an area 3 times the size of the full moon, probing infrared depths no survey had ever reached. When that survey's data began flowing in, the numbers inside it would make even the Hubble Ultra Deep Field feel, by comparison, like a glance through a pinhole. Designing the most sweeping survey ever attempted with the most expensive telescope ever built is exactly as demanding as it sounds. The debates over how to approach it stretched on for years before a single pixel was recorded. The survey, ultimately named CosmosWeb, grew from a competitive selection process in which research teams around the world submitted proposals for how the James Webb Space Telescope's first cycle of general observing time should be divided. Time on the telescope is calculated in hours, and those hours are genuinely limited. Every hour devoted to one target is an hour withheld from another. The teams advocating for a wide-area survey had to persuade the scientific community that covering a broad expanse of sky in depth was worth forgoing everything else. They were awarded 255 hours. The co-principal investigators, Jehan Kartaltepe of the Rochester Institute of Technology and Caitlin Casey of the University of California, Santa Barbara, led a team that mapped a region of sky roughly 3 times the width of the full moon. They employed Webb's near-infrared camera to image 0.54 square degrees of the cosmos field, a region in the constellation Sextans that had been surveyed by dozens of observatories over the preceding 2 decades and was selected specifically because such a wealth of existing data was available for comparison. The technique required stitching together more than 10,000 individual frames into a single coherent mosaic. The process demanded years of calibration, testing, and refinement even before launch. The data itself arrived in successive waves, each requiring immense computational effort to process and integrate with what preceded it. In June 2025, the team released the complete Cosmos Webb 2025 catalog. It contained nearly 800,000 galaxies, each measured across 37 photometric bands, meaning each galaxy was recorded at 37 distinct wavelengths of light. The combination of those measurements allowed researchers to determine not just each galaxy's position on the sky, but its distance, the age of its stars, its rate of new star production, and how much dust it harbored. Maximilien Franco of the Université Paris-Saclay, who directed the imaging analysis, described the experience of watching previously invisible galaxies materialize on the monitors for the first time. He said it was remarkable to uncover objects that had been entirely hidden at other wavelengths, and deeply satisfying to finally see them emerge on screen after years of preparation. The scale of the catalog is genuinely difficult to hold in mind all at once. 800,000 galaxies, every one containing hundreds of billions of stars. If you printed the Cosmos Webb mosaic at the resolution of a standard newspaper, the image would cover a surface the area of a full football pitch. Every smear, every blur, every barely resolved speck in that printout would be an entire galaxy. The survey spans cosmic history from relatively nearby objects to galaxies that existed when the universe was barely 7% of its present age. In a single mosaic, researchers captured nearly all of the 13.8 billion years of the observable universe's existence. And the scientists who assembled the catalog already knew that the most startling objects inside it had not yet been identified. Behind every landmark scientific achievement, a team of people spends years solving problems that will never make headlines. The Cosmos Webb catalog is no different. Converting 10,000 raw telescope images into a usable scientific catalog is not glamorous labor. It involves locating and removing artifacts left by cosmic rays striking the telescope's detectors, correcting for the fact that each of the 37 photometric bands was acquired at slightly different times with slightly different instrument settings, and building a consistent coordinate framework so that a galaxy identified in one filter aligns precisely with its counterpart across all the others. A single misalignment, even by a fraction of a pixel, can distort a measurement of an object's color, and a distorted color can produce an entirely wrong distance estimate. Marco Schuntov of the Cosmic Dawn Center in Copenhagen directed the effort to build the catalog itself. The catalog, known as Cosmos Web 2025, is what converts a mosaic of images into a scientific instrument. Each of the nearly 800,000 entries represents a galaxy with a measured set of attributes: position, brightness across each of the 37 bands, estimated distance, estimated stellar mass, estimated star formation rate, and several dozen additional quantities. The catalog is what allows researchers worldwide, many of whom played no part in the original survey, to interrogate the data and extract answers. Maximilian Franco managed the imaging pipeline, the sequence of computational procedures that transformed raw detector outputs into the final calibrated frames. He described the challenge of revealing galaxies invisible at every other wavelength, objects that appeared only when Webb's deep infrared sensitivity was applied. Some of those galaxies had shown up in earlier surveys of the cosmos field as faint, unresolved patches, or had been entirely absent. In Webb's infrared data, they emerged with a richness of detail that prior generations of astronomers had no means to foresee. The team combined observations not just from Webb's near-infrared camera, but from multiple instruments, including the mid-infrared instrument, along with archival data from the Hubble Space Telescope, the Subaru telescope on Mauna Kea, and the Very Large Telescope in Chile. The layering of those observations, each spanning different wavelength ranges and different sensitivity limits, produced a portrait of the galaxy population across cosmic time richer than any previously assembled. The survey encompasses galaxies from redshift 0.1, relatively nearby on a cosmic scale, all the way to redshift 12, corresponding to galaxies that existed when the universe was roughly 3% of its current age. That range means the catalog spans essentially the entire history of visible structure in the universe, from comparatively mature galaxies actively forming stars today to the first recognizable forerunners of modern galaxy clusters. The scientific papers emerging from Cosmos Web across 2024 and 2025 are simultaneously revising multiple chapters of galaxy formation theory. What the architects of the map understood, and had been careful not to announce too loudly until the data confirmed it, was that the catalog contained objects with no explanation in the standard models. Galaxies too massive, too luminous, and too chemically mature to have assembled in the time available. The map had been constructed. Now came the harder task of understanding what it was actually showing. While Cosmos Web was being planned to survey as wide a field as possible, a separate team took the opposite approach. They fixed on a single target, one of the most extreme concentrations of mass in the known universe, and stared at it until it yielded things no other strategy could access. Abell 2744 is known among astronomers as Pandora's cluster, a name earned because every careful examination of it turns up something unexpected. It is a merging system, several immense galaxy clusters that collided and are still in the process of interpenetrating. Their gas clouds crash together at millions of miles per hour, while their galaxies and dark matter halos overlap in a gravitational collision that has been underway for billions of years. The product is an object of almost unrivaled mass packed into a compact region of sky. That mass makes it one of the most powerful natural telescopes in the observable universe. A program called UNCOVER, short for Ultra-Deep NIR Spec and NIR CAM observations before the epoch of Ryanization, targeted this cluster specifically because of what its gravity could do to light originating behind it. The lensing, produced by Pandora's cluster, is not uniform. The multiple merging subclusters create overlapping zones of gravitational distortion, each bending light from different directions at different magnifications, effectively generating dozens of separate gravitational lenses layered atop one another. The UNCOVER team reached observation depths of approximately 32 magnitudes in the lensed region. The faintest objects they detected were emitting so little light that, without the cluster's amplification, no telescope in human history could have registered them. In practical terms, the cluster was functioning as an additional telescope hundreds of meters across, stacked in front of Webb's own 6.5-meter primary mirror. Spectroscopic follow-up, which involves spreading an object's light into its constituent wavelengths to pin down its distance precisely, was obtained for nearly 700 objects within the survey area. Those objects ranged from galaxies at redshift 0.3, relatively close on a cosmic scale, to objects at redshift 13, placing them within the universe's first few hundred million years. What emerged from that spectroscopic campaign was a picture of galaxy evolution, spanning almost the complete history of the observable universe, all gathered through a single extraordinary gravitational lens. Some of the most distant objects in the UNCOVER sample were entirely absent from prior surveys, including those conducted by the Hubble Space Telescope across multiple decades. They had existed in the data all along, invisible, waiting for a sufficiently sensitive instrument combined with a sufficiently powerful natural lens to bring them into view. The extreme magnification available through Pandora's cluster also allowed scientists to examine the internal structure of early galaxies at a resolution impossible in unlensed fields. They could measure star formation rates in individual regions of a galaxy that existed when the universe was less than 5% of its current age. They could assess whether those galaxies had central concentrations or were more loosely distributed. They could begin asking whether the structures assembling in the first billion years resemble anything visible today. In many cases, the answer was that they do not, and the reasons why continue to be debated at conferences around the world. The name comes from an Old Norse word meaning rising light, and it was chosen deliberately because the object it describes reached human instruments after a journey lasting nearly 13 billion years. Earendel is a star, a single star, or what appears to be one, residing in a galaxy called the Sunrise Arc, at a redshift of approximately 6.2. In terms of cosmic time, the light from Earendel departed when the universe was less than 1 billion years old, at a period when the first generations of massive stars were living and dying at extraordinary rates, seeding the cosmos with heavy elements that would eventually make planets like Earth possible. It should be undetectable. Individual stars at such distances produce so little light that even the James Webb Space Telescope, the most sensitive instrument humanity has ever constructed, cannot ordinarily register them. The nearest stars beyond our own galaxy already lie at the frontier of individual stellar resolution for the most capable ground-based telescopes. The prospect of detecting a single star billions of light-years distant, from an era before the universe had finished becoming transparent, seemed physically impossible for most of the 20th century. What made Earendel visible was a geometric coincidence so precise that scientists initially struggled to accept it. The sunrise arc lies behind a galaxy cluster designated WHL0137, sitting about 5.5 billion light-years from Earth. That cluster bends and amplifies light from the galaxy behind it, just as Pandora's cluster amplifies its background sources. But at the moment, astronomers observed Earendel with the Hubble Space Telescope in 2022. Something extraordinary was occurring. The star happened to be positioned almost exactly on the gravitational caustic of that cluster, the arc of maximum magnification where the lensing effect peaks. At that alignment, the amplification of Earendel's light rose to levels that made the detection possible. Estimates of the actual magnification varied considerably, but the enhancement was staggering, potentially tens of thousands of times. That magnification is what rendered a star from the universe's first billion years detectable by instruments orbiting a planet that had not yet formed when the star was burning. Follow-up observations with the James Webb Space Telescope measured the star's spectrum with greater precision. What came back was not the clean signature of a single hot star. The data pointed toward something more complex, possibly a binary system. Two stars in mutual orbit, with temperatures ranging from roughly 9,000 to 34,000 Kelvin. The cooler of the two would be comparable to some of the most massive stellar objects known in the nearby universe. The hotter would be near the upper boundary of stellar temperatures. At the moment of its discovery, Earendel held the title of the most distant individual stellar object ever resolved by human instruments. Then, in 2025, a paper appeared that challenged everything the field had concluded about what Earendel actually was. The challenge did not originate outside the scientific mainstream. It came from a team with direct access to the same James Webb Space Telescope data, and the argument they advanced was detailed, systematic, and not easily dismissed. Massimo Pascal and colleagues at the University of California, Berkeley published their challenge in the Astrophysical Journal Letters in July 2025. The central claim was simple to state, though the implications required time to absorb. What if Earendel is not a single star at all? The alternative they put forward was that the object is a compact, ancient star cluster, specifically a metal-poor globular cluster progenitor, one of the dense, tightly bound assemblages of hundreds of thousands of stars that formed inside the earliest galaxies and whose descendants orbit the Milky Way today as the ancient globular clusters visible through any backyard telescope. If this reading is correct, the most distant individual stellar object ever identified is actually a compact stellar system, not a solitary star. The argument rested on several strands of evidence drawn from James Webb Space Telescope spectra and from comparisons with other objects along the same gravitational arc. The first strand involved metallicity, the abundance of elements heavier than hydrogen and helium recoverable from the object's light. Earendel's spectral properties fall within the range expected for very metal-poor stellar populations, consistent with globular cluster progenitors from the early universe, though this alone does not distinguish between a single star and a dense cluster of them. The sharper argument came from comparing Earendel with another source in the same lensed arc, a separate object whose angular size and brightness had already led researchers to identify it as a star cluster. Pascal's team argued that Earendel shares enough properties with that confirmed cluster, in terms of stellar surface density, estimated age, and behavior across different wavelengths, that the more economical interpretation is that both objects belong to the same class. The operative word in that argument is economical. The gravitational magnification that made Arundel visible is extreme, but extreme magnification also carries large uncertainty in the actual amplification factor. If the true magnification falls at the lower end of the estimated range, a single star would produce far too little light to account for what Webb recorded. A compact cluster of 1,000,000 or more stars, even at very low metallicity, would present no such difficulty. Scientists working on Arundel have responded that the question remains unresolved. The magnification estimates carry enough uncertainty to accommodate both interpretations, and certain features of the data are more naturally explained by a single stellar source. The debate is ongoing, and a definitive answer will require additional observations not yet scheduled. What is clear, regardless of the outcome, is the window Arundel opens onto the early universe. Whether it is a solitary massive star or a compact ancestor of the globular clusters orbiting ancient galaxies today, it represents a measurement at a distance and an epoch that would have seemed like science fiction 20 years ago. The frontier of individual stellar detection has been extended to a point in the universe where the very first stars were forming. And in 2024, a separate team had already found something in that same early universe that would be, in some respects, even more extraordinary. Angela Adamo spent years preparing for the moment when the James Webb Space Telescope images of a particular lensed galaxy would arrive on her computers. She was still astonished. Adamo leads a research group at Stockholm University focused on how star clusters are born, grow, and endure across cosmic history. Her team targeted a gravitationally lensed galaxy called the Cosmic Gems Arc, located behind a foreground cluster at a redshift of approximately 10.2. That redshift places the background galaxy 460 million years after the Big Bang, in the heart of the earliest era of organized star formation in the observable universe. The lensing magnification was high, and Webb's resolution was sufficient to peer into the galaxy's interior at scales no earlier observation could reach. When the images emerged from the pipeline and the team sat down to examine them, Adamo has described the experience as a sequence of small shocks arriving in rapid succession. Inside a region spanning fewer than 230 light-years across, the team resolved 5 compact objects, 5 distinct concentrations of stars, each measuring only about 3 light-years in true diameter, each containing approximately 1,000,000 solar masses. Those 5 objects became known as the Cosmic Gems. The findings were published in the journal Nature in June 2024. The stellar density of these clusters is the figure that most clearly communicates what makes them so remarkable. Star clusters in the nearby universe, including younger ones forming in actively star-forming galaxies today, have stellar surface densities ranging from a few hundred to a few thousand solar masses per square light-year. The Cosmic Gems clusters have stellar surface densities 1,000 times higher than the densest young star clusters observed anywhere in the local universe. They are packed to a degree that appears essentially nowhere in the galaxy population surrounding us today. At such densities, something important happens. Massive stars press together closely enough to interact gravitationally on timescales shorter than their individual lifetimes. Runaway mergers become possible, with star after star falling into a growing central mass until the product is something too large to have formed through ordinary stellar evolution. That pathway is one proposed mechanism for generating intermediate mass black holes, whose existence has long been inferred, but whose formation process has never been directly witnessed. The cosmic gems clusters are younger than 50 million years, as measured from their stellar populations. Their metallicity is less than 1% of that of our own galaxy, consistent with objects forming in the earliest stages of chemical enrichment in the cosmos. Their masses and densities match what theorists have long predicted the ancestral globular clusters should look like before billions of years of dynamical evolution thinned and softened them into the ancient systems orbiting the Milky Way today. Larry Bradley of the Space Telescope Science Institute, who contributed to the analysis, stated plainly that no other telescope could have made this discovery. That is accurate. Without the combination of Webb's infrared sensitivity and the foreground cluster's gravitational magnification, these 5 objects would remain invisible, embedded in data no one would know how to decode. What those 5 clusters represent is the possibility of witnessing the birth of structures that have accompanied us in evolved form throughout the entire history of the galaxy, observed here at their origin 460 million years after everything began. The story was about to expand in scale by orders of magnitude. The cosmic vine was concealed inside data from a survey called the Cosmic Evolution Early Release Science Field, buried within a catalog of galaxy redshifts that researchers were still working through in late 2023. What Shuowen Jin and colleagues at the Cosmic Dawn Center in Copenhagen were searching for was any pattern in the redshift distribution suggesting galaxies congregating at the same distance. The technique is straightforward in principle. If you measure the spectroscopic distance to hundreds of galaxies in the same patch of sky, and find that many fall at nearly identical redshifts, you are probably seeing a genuine structure rather than a random scatter. Galaxies at the same redshift lie at the same distance. Galaxies at the same distance appearing close together on the sky are, in 3 dimensions, genuinely close to each other in space. What Jin found was 20 galaxies with confirmed spectroscopic redshifts, all gathered between redshift 3.434 and redshift 3.45. That places them about 2 billion years after the Big Bang, in a period of intense galaxy formation when the largest structures in the universe were still consolidating from smaller pieces. But 20 galaxies is only the confirmed core. Further analysis identified approximately 200 candidate members surrounding that core, spread across a region of sky that, when translated into physical distances at that redshift, produced a structure roughly 13 million light-years long and only about 650,000 light-years wide. The shape gave it its name. The 20 confirmed galaxies and their surrounding halo of candidates trace a long, slender filament, like a vine stretching across the early universe, with its 2 most massive galaxies anchored near the center. Those 2 central galaxies each contain about 800 billion solar masses. That is an enormous stellar mass for objects that existed only 2 billion years after the Big Bang. But the mass was not what most surprised the team. What surprised them was that both galaxies had already ceased forming stars, in an environment brimming with activity, in a large-scale structure actively accumulating mass and surrounded by hundreds of star-forming galaxies. The 2 largest members of the vine had gone quiet. Their stellar populations were old. Their star formation rates had fallen to effectively 0. Their shapes were dominated by central bulges rather than extended disks. They looked, in other words, like the old red ellipticals common in massive clusters in the nearby universe today. The nearby universe is 13.8 billion years old. These galaxies had reached that state in just 2 billion years. The simulations cosmologists run to model large-scale structure suggest that the cosmic vine will continue evolving, drawing in additional material from its surrounding environment and eventually collapsing into a virialized galaxy cluster with a total mass exceeding 100 trillion solar masses, comparable in scale to the great clusters visible in the modern universe. That collapse has not yet occurred in any data we possess. What the James Webb Space Telescope data is capturing is the process mid-formation, already generating surprises no model anticipated. And 2 billion years deeper into the past, something even larger was already taking shape. In January 2026, a paper appeared in the journal Nature describing something astronomers had not expected to encounter for many years to come. The team was led by Akos Bogdan of the Center for Astrophysics at Harvard and Smithsonian. The object under report was a protocluster, a galaxy cluster in the act of forming, located 12.7 billion light-years from Earth. At that distance, the light entering Webb's detectors had departed its source when the universe was barely past its first billion years. The structure is designated JD1, and it may be the most distant confirmed galaxy cluster core ever detected. It contains at least 66 candidate galaxy members visible in James Webb Space Telescope imaging, a dense concentration gathered within a compact region of sky. Its total mass, including the dark matter halo in which those galaxies are embedded, is estimated at approximately 20 trillion solar masses. That is not the mass of a single large galaxy. That is the mass of an entire galaxy cluster assembled when the universe was less than 8% of its present age. But the mass alone was not what made JD1 the focus of urgent scientific discussion. What elevated it to front-page news in astrophysics was what the Chandra X-ray Observatory recorded when it was directed at the same location. Chandra sees the universe in X-ray light, the extremely high-energy radiation produced by matter heated to temperatures of millions of degrees. When galaxy clusters reach sufficient mass, they contain enormous quantities of gas that has plunged toward the cluster's center and been shock-heated to those extreme temperatures. This incandescent gas fills the spaces between galaxies in a mature cluster and generates a distinctive X-ray signature, allowing astronomers to confirm that a cluster's mass is truly concentrated and gravitationally bound, rather than a chance alignment of unrelated objects at varying distances. Chandra detected that signature at the location of JD1, a cloud of gas heated to millions of degrees sitting within the structure, confirming that the cluster is real, that its mass is genuinely concentrated, and that the physical processes of cluster formation are already well advanced. The difficulty is that standard models of cosmological structure formation predict that galaxy clusters of this mass should not begin appearing until the universe is considerably older. Assembling 20 trillion solar masses into a gravitationally bound structure requires conditions that, according to those models, did not yet exist at the epoch when this cluster is observed. Bogdan described the finding as evidence that the universe was in an extraordinary hurry to grow up, a phrase that captured a feeling widespread in the observational community by early 2026. His co-author, Garrett Schellenberger, offered a different image. He likened the observation to watching an assembly line build a car in real time, rather than trying to understand how a car functions by examining only the finished product. The cluster was assembling itself in front of the telescope, seen across a delay of 12.7 billion years. What JD1 disclosed was that the scale of structure in the early universe was not merely surprising at the level of individual galaxies. It was surprising at the level of the largest gravitationally bound objects in existence. A discovery of this kind does not stand alone. It connects to a growing pattern in the data, a pattern implying that something in our understanding of cosmic origins is fundamentally unfinished. And the most dramatic component of that pattern was still waiting to be revealed. For a brief window in the spring of 2024, a galaxy from the JD's survey held a title no one expected to be claimed: the most distant confirmed galaxy in the known universe. A genuine record from the edge of everything detectable. Scientists had been stunned by its existence. The data had been checked and rechecked. It held. Then, 12 months later, someone surpassed it. In May 2025, a team at Yale University announced the discovery of a galaxy that reached further back in time than anything before it. Its designation was MOM-Z14, short for Mother of Miracles, drawn from the survey that found it. When you understand what it represents, that name feels entirely fitting. Its light left the galaxy 280 million years after the Big Bang. It had been in transit toward us for 13.5 billion years. Peter van Dokkum, professor of astronomy and physics at Yale, led the team that extracted it from the data. The galaxy had been waiting inside the enormous Cosmos Web mosaic to be found. Its signature was unmistakable once you knew what to look for. Short wavelengths of light, the kind produced by hydrogen gas, had been completely absorbed by the ancient neutral gas surrounding the galaxy before they could escape into open space. The galaxy shone brightly at longer infrared wavelengths, but vanished entirely at the blue end of the spectrum. That dropout pattern is the fingerprint of extreme distance. Every galaxy at such depths wears the same mask. MOM-Z14 is tiny, only about 500 light-years across. For comparison, the Milky Way spans roughly 100,000 light-years. This galaxy could tuck itself into the space between our nearest few hundred star clusters and disappear. And yet, from that impossibly compact volume, it blazes across 13.5 billion years of space and still arrives at Webb's mirror, still detectable. That luminosity demands either an extraordinary concentration of newborn stars or something else entirely. When the team searched for signs of a central supermassive black hole feeding on surrounding gas and contributing its own glow, they found nothing. This galaxy's brilliance comes entirely from stars being born at a furious pace. Van Dokkum gave an interview after the announcement and reached for a comparison to give the timescales some texture. Sharks, he pointed out, have been swimming in Earth's oceans for longer than the age of this galaxy at the moment its light was emitted. The ocean predators that predate every major mass extinction in Earth's history represent a greater span of continuous existence than the entire lifespan of MOM-Z14. At the moment Webb photographed it, that comparison lands differently than most astronomical analogies. It places deep time inside something living and breathing, rather than something geological and cold. Van Dokkum added a remark that should give you pause. Webb, he said, was not supposed to discover any galaxies this early in the history of the universe. Not at this stage in the mission. The discovery pipeline had been calibrated around expectations of rarity at extreme distances. Those expectations, one after another, have been overturned. By early 2026, more than 100, Galaxies comparable to MOM-Z14 had been catalogued from just the first 400 million years after the Big Bang. The number grows with every fresh pass through Webb's data. Astronomers anticipated a handful of faint, primitive smudges from this era. What they are finding looks increasingly like a crowd, and that crowd is doing something the entire theoretical edifice of modern cosmology was designed to prevent. The oxygen should not have been there. That was the immediate reaction of Renske Schmidt of the Leiden Observatory when the data came through from the ALMA radio telescope array. The measurement showed 10 times more oxygen than any reasonable model predicted a galaxy could have manufactured in the time it had existed. The result appeared in early 2025, published simultaneously by two independent research teams that had reached identical conclusions working from the same data by entirely separate methods. Confirmation from two groups at once made the result essentially impossible to set aside. To appreciate why oxygen is so extraordinary at this distance and depth, you need to understand where oxygen comes from. It is forged inside massive stars through nuclear fusion. The Big Bang produced hydrogen and helium almost exclusively. Every atom of oxygen in your body, in Earth's oceans, in the air you breathe, was synthesized inside a star that lived and died before our solar system was born. When a massive star exhausts its fuel and detonates as a supernova, it disperses those freshly forged heavy elements back into the surrounding gas. The next generation of stars and eventually planets forms from that enriched material. That process takes time. Stars must be born. They must consume their fuel, which takes millions to tens of millions of years, even for the most massive. Then they must die and explode and scatter their interiors. Then the next generation must form. For a galaxy that existed only 290 million years after the Big Bang to contain 10 times more oxygen than expected, multiple complete cycles of stellar birth and death had already run to completion inside it. Multiple generations of massive stars had lived and died, each one enriching the raw gas available to the next, each death seeding the galaxy with progressively heavier elements. Schmidt described the discovery as finding an adolescent where you expected only infants. The galaxy was already chemically mature in a universe barely past its birth. The second team, led by Stefano Carniani of the Scuola Normale Superiore in Pisa, published their complementary findings at the same moment. They were equally astonished. The evidence, Carniani said, opened a new perspective on the earliest phases of galaxy evolution that no one had been prepared for. A galaxy could reach this level of chemical sophistication this quickly. The enrichment that took the Milky Way billions of years to accumulate had already occurred in a fraction of that time inside this compact, blazing object. There is a precision detail here that deserves its own moment. The ALMA measurement of the galaxy's distance achieved accuracy to within a fraction of a percent. That is the equivalent of measuring a kilometer and being accurate to within 5 centimeters, accomplished at a distance of 13.5 billion light-years with a radio telescope on the ground. What this detection forces onto the table is a problem far larger than any single galaxy. If that ancient object was already chemically mature before the universe reached 300 million years of age, then the stars responsible for all that enrichment had to be forming, living, and dying in the first 200 million years or less. The earliest sliver of cosmic time pushes the opening chapter of stellar history far earlier than any model had forecast. And that is when the crisis in cosmology ceases to be about individual galaxies and starts being about the entire theoretical framework, the standard, cosmological model is one of the most successful scientific theories ever developed. It describes how the Big Bang produced a nearly uniform universe, how minuscule quantum fluctuations in density seeded the first structures, how gravity amplified those seeds into concentrations of dark matter, how gas fell into those concentrations and fragmented into the first stars, how those stars gathered into the first galaxies hundreds of millions of years later. The model is supported by decades of observation and makes precise predictions across an enormous range of cosmic scales. Most cosmologists regard it as one of humanity's supreme intellectual achievements. Webb has spent 3 years finding objects the model says should not exist. The difficulty began accumulating before MOM-Z14. As the telescope was turned toward deep fields and gravitational lenses and began compiling galaxies at extreme distances, a pattern emerged. The galaxies being found were too massive, too luminous, too chemically developed. They contained too many stars for their age, too much chemical enrichment, too much organized structure. At every distance where the model had made confident predictions about what should be present, Webb kept finding something more. Michael Boylan Colchin of the University of Texas at Austin worked through the numbers carefully and published the result. Some of the massive galaxies Webb found at the highest redshifts require star formation efficiencies of 50% or higher to have assembled their stellar mass within the time available. In the present-day universe, the fraction of available gas that actually converts into stars typically falls between 1 and 5%. The standard model predicts a theoretical ceiling of 10 to 20%, under the most favorable conditions ever modeled. Reaching 50% requires conditions the existing framework has no mechanism to generate. Some galaxies, Boylan-Colchin calculated, appear to require efficiencies approaching 100%. Every available atom of gas converted into stars almost instantaneously on cosmic timescales, with no waste, no suppression, no physical process throttling the conversion. The established physics of star formation should make that impossible. Supernovae alone should disrupt a galaxy's gas supply long before efficiency approaches such levels. The problem has a second dimension beyond efficiency. These galaxies are enormous. Their stellar masses are hundreds of millions to billions of times the mass of a typical star. Assembling that much stellar mass within 200 million years demands a rate of star formation so extreme it strains every calibrated measurement astronomers have obtained from the local universe. Webb was built to see far. What it has seen is raising questions that extend well beyond its engineering specifications. What is occurring in the early universe that our models have failed to capture? And does the model need adjustment or something more fundamental? When the impossible galaxies continued to appear, cosmologists did not abandon their framework immediately. That would have been premature. Instead, they began proposing mechanisms that could account for the observations within or just beyond the limits of existing theory. The resulting set of proposals is more illuminating than any single answer would have been. The leading candidate is called feedback-free star formation. In the present-day universe, massive stars are extraordinarily destructive. They blast out radiation that ionizes surrounding gas. When they die in supernova explosions, the shock waves heat their environment and drive material away from regions where new stars might otherwise form. This feedback loop is essentially self-limiting. Stars form, become disruptive, and suppress the formation of subsequent generations around them. In the very early universe, conditions may have been different in a specific and consequential way. The first galaxies formed from gas containing almost no heavy elements. Metal-free gas cools and fragments differently. Some theoretical models suggest that in this early window, galaxy-scale star formation could proceed at efficiencies approaching the theoretical maximum before the destructive effects of the first supernova explosions had time to propagate through the host galaxy. The feedback mechanism existed, but it had not yet had time to take effect. A second proposed explanation concerns the nature of the first stars themselves. The very first generation, formed from pure hydrogen and helium, may have been far more massive than typical stars today. More massive stars produce more ultraviolet light per unit of mass. If early galaxies were populated predominantly by these enormous primordial stars, the galaxies would appear far brighter and more massive than they actually were. Webb might in some instances be detecting an optical illusion. A galaxy whose apparent luminosity is inflated by a stellar population unlike anything in the modern universe. A third possibility involves contamination by actively accreting supermassive black holes. Some extraordinarily luminous galaxies may harbor compact central black holes, consuming surrounding gas and contributing their own intense radiation to the galaxy's total output. Follow-up studies have confirmed this in some of the most extreme cases, though it does not account for all of them. A fourth candidate involves the scarcity of dust. Early galaxies may have contained far less dust than modern ones. In the present universe, dust absorbs a substantial fraction of the ultraviolet radiation produced by newly formed stars. If early galaxies were effectively dust-free, that radiation escaped unimpeded, making those galaxies appear more luminous than their true star formation rates would justify. A minority of theorists have proposed something more fundamental: modifications to the behavior of dark matter or dark energy in the early universe that would allow structure to assemble faster than the standard framework predicts. These proposals face serious constraints from other observations. None of these explanations is fully satisfying on its own. The truth likely involves several working in combination. But before anyone declares the crisis resolved, the skeptics have something indispensable to say. Science advances by subjecting its most dramatic claims to unrelenting scrutiny, until only those that survive remain standing. The impossible galaxies are no exception, and the examination they have received over the past 3 years has already revised some of the most extreme initial announcements downward. Most cosmologists working in this field do not believe the standard model is broken. They believe it is under stress. They believe our understanding of early star formation physics is incomplete. They also believe, based on years of experience with Webb data, that some fraction of the most alarming, early claims will prove to have been overstated. That process of revision has already begun. In the first 2 years of Webb operations, several galaxies heralded as extraordinary distance records were subsequently found to have been misidentified. The technique used to estimate galaxy distances from imaging data alone, called photometric redshift modeling, works by matching a galaxy's brightness profile across multiple wavelengths to a library of theoretical templates. It is powerful and often reliable. It is also fallible in ways that matter greatly at extreme distances. A galaxy at a relatively modest distance that happens to be very red can mimic the dropout signature of an extremely distant galaxy in certain filter combinations. When spectroscopic follow-up, which directly measures the wavelengths of specific atomic emission lines and yields far more dependable distance estimates, was applied to some high-profile early candidates, the distances came back dramatically lower. This is the process functioning as designed. Photometric redshifts are screening tools. Spectroscopy is confirmation. The genuine distance records that remain standing, the ones that have withstood spectroscopic verification, are locked in. The rest were drafts, not discoveries. The deeper theoretical gap deserves honest assessment as well. The discrepancy between what the standard model predicts and what Webb observes is real. It is statistically significant. It has persisted as better data arrived. The gap might reflect the model's need for revision in its treatment of early star formation efficiency. It might reflect something more fundamental. It might also reflect selection effects, where Webb preferentially detects the rarest, brightest objects at extreme distances, while the more typical population at those redshifts remains too faint to catalog. One published review from early 2026 summarized the expert consensus plainly. It is premature to declare the standard model broken. The AI observations are extraordinary. The discrepancies are genuine. The work continues. Drawing final conclusions at this stage would be rash. Science under pressure can resemble crisis and later disclose itself as progress. That summary was written before one of the strangest and most philosophically striking results of the Webb era appeared in print. A result that showed for the very first time the invisible architecture holding everything together. Diana Scognamiglio had been working toward a map that should have been impossible to make. Dark matter emits nothing, reflects nothing, and absorbs nothing. It interacts with ordinary matter only through gravity. No camera can photograph it. No spectrograph can fingerprint it. It produces no wavelength of light for any detector to capture. Every dark matter map ever assembled has been a reconstruction, an inference drawn from the gravitational signatures dark matter imprints on things that can be seen. For years, those reconstructions had been blurry. Scognamiglio, a researcher at NASA's Jet Propulsion Laboratory, wanted to change that. In January 2026, the result appeared in the journal Nature Astronomy. It was the sharpest and most detailed dark matter map ever produced from space-based data, covering a region of sky roughly 2.5 times the area of the full moon. The map was constructed from the same Cosmos Web survey data that had yielded MOM-Z14 and the catalog of nearly 800,000 galaxies. Within that patch of sky, Scognamiglio's team used approximately 250,000 background galaxies as probes, tracing the distribution of invisible mass with a clarity no previous instrument had achieved over a comparable area. The numbers describing this achievement require a pause. The map is twice as sharp as any earlier space-based dark matter map at this scale. It traces mass concentrations corresponding to 129 galaxies per square arc-minute of sky, nearly double the density achievable by the Hubble Space Telescope. It reaches back to when the universe was approximately 3 billion years old, the peak era of cosmic star formation. And it resolves structures that previous maps had fused into featureless blurs. Scognamiglio described the experience of comparing this map to earlier versions as moving from a watercolor sketch to a high-resolution photograph. The structures were always there. Now their details are legible. When the first side-by-side comparison slide was displayed at a Cosmos Research Collaboration meeting in May 2025, placing the older Hubble-era dark matter map of this region alongside the new Webb-era version, the room did something unusual for a scientific conference. People began applauding. Scognamiglio later described it as recognition rather than celebration. Scientists saw something they had not expected to be achievable yet, and responded in the only way that felt right. The map reveals a structure that has been theorized for decades, but never seen at this resolution. A network, an architecture, the invisible skeleton on which every visible thing in the universe is arranged. And once you understand what that skeleton looks like and why it exists, the universe becomes a fundamentally different place to inhabit. Nothing in the cosmos occupies its position by accident. Every galaxy, every cluster, every thread of stars linking one dense node to another sits where it does because dark matter pulled the surrounding gas there first, quietly and invisibly across billions of years. The dark matter map, built from Cosmos Web data, reveals this scaffolding with enough clarity to trace individual strands of the web. And understanding how the map was constructed is nearly as striking as what it shows. The method is called weak gravitational lensing. Consider a galaxy 10 billion light-years away. Between that galaxy and Webb's mirror lies a vast, invisible architecture of dark matter, distributed across hundreds of millions of light-years. None of it radiates light, but its gravity bends the paths of light passing through it, and that bending distorts ever so slightly the apparent shape of the distant galaxy, as seen from Earth. The distortion is minute, a fraction of a percent of the galaxy's total apparent size. On any single galaxy, the effect is entirely undetectable against the natural diversity in how galaxies are shaped. This is where statistics rescues the measurement. When you analyze 250,000 background galaxies simultaneously and search for coherent patterns in their distortions, the dark matter signal rises out of the noise. Galaxies lying behind a dense region of dark matter are all distorted in a consistent direction. By charting where these correlated distortions appear across the survey, you reconstruct where the invisible mass concentrations lie. You build a map of what cannot be seen from the echoes it leaves in what can. What the map reveals is not a smooth, uniform distribution of dark matter. It shows peaks where galaxy clusters reside, their massive dark matter halos commanding the local gravitational landscape. Connecting those peaks, elongated filaments of moderate density stretch across tens of millions of light-years. Between the filaments, enormous voids lie nearly empty of mass, regions that galaxies have abandoned almost entirely. This is the cosmic web. Computer simulations had forecast its existence for 40 years. Galaxy redshift surveys had sketched its outlines by tracing the distribution of visible matter. The January 2026 map is the first time its dark matter backbone has been resolved at this level of detail in a space-based observation. And the resolution matters enormously. Faint galaxy groups previously swallowed by the blur of earlier maps now emerge clearly. Filaments that had seemed to converge into one another separate into distinct structures. The hidden architecture of the universe is at last visible. Emily Linder of the Illinois Institute of Technology captured the essential strangeness of this result. Dark matter, she noted, represents 85% of all mass in the universe. We do not know what it is, and until very recently, we could barely perceive where it was. JWST has changed that, and what it reveals is a universe that is organized rather than random, structured rather than scattered, woven rather than spilled. That organization is what makes the next number so difficult to absorb. Christopher Consolis had a problem with the galaxy count, and the galaxy count had been wrong for over 20 years before he found and corrected the error. The original figure, somewhere between 100 billion and 200 billion galaxies in the observable universe, derived from a calculation performed after the Hubble Space Telescope completed its deep field observations in the 1990s. Researchers counted the galaxies visible in a tiny patch of sky, projected that density across the full celestial sphere, and arrived at a figure that seemed almost incomprehensibly large: 200 billion galaxies. That number entered textbooks, scientific reviews, documentaries, and public consciousness as settled fact. Consolis, an astronomer at the University of Nottingham, spent years building three-dimensional models of how galaxy populations evolve through cosmic time and recognized that the straightforward extrapolation from deep field images was missing something essential. The most distant, faintest galaxies of the early universe, the small, numerous objects that dominated the first billion years of cosmic history, lay simply below the detection threshold of every telescope ever built. They were real. They were out there. They were sending light that crossed billions of light years toward Earth, then fell just short of triggering any detector. They had never been counted. When Consolis's team published their revised calculation in 2016, the corrected total came out closer to 2 trillion galaxies, 10 to 20 times higher than the previous estimate. More than 90% of all galaxies in the observable universe had been invisible to human instruments and therefore absent from every census. 2 trillion. Consolis offered a comparison to give the number human scale. 2 trillion is roughly the number of seconds in 1,000 average human lifetimes. Counting at one galaxy per second, without pause, without sleep, would take 63,000 years to reach 2 trillion. Human civilization, from the earliest writing to the present, spans approximately 10,000 years. The count would not be finished within the entire recorded span of human history. Consolis noted at the time that JWST was the instrument most likely to begin revealing this hidden population. The Cosmos Web Catalog, with its nearly 800,000 galaxies spanning most of cosmic history, represents an early step in that direction. Extrapolate its galaxy density across the entire sky, and you arrive at a number consistent with 2 trillion. More than 90% of those galaxies have never been observed by any instrument built by any civilization on this planet. Most have never been photographed. Most have never been named. Most will require telescopes that do not yet exist to detect it all. There are 2 trillion galaxies in the observable universe. Each one is an island universe unto itself, and every one of them is composed of something that dwarfs every other quantity in this story. The number of stars in the observable universe defeats intuition entirely. It exceeds by orders of magnitude every quantity that appears in ordinary experience. It exceeds the national debt of any nation by a factor that renders the comparison meaningless. It exceeds the number of cells in a human body by approximately 1 billion times. The conservative estimate is 10 to the 24th power, written out as the number 10 septillion, a 1 followed by 24 zeros. Astronomers arrived at this figure by combining the estimated number of galaxies with the estimated average number of stars per galaxy, accounting for the full spectrum of galaxy sizes from massive spirals to the dwarf galaxies that make up the majority of the actual cosmic population. The comparison that gives this figure shape involves sand. Every beach on Earth, every desert, every volcanic shoreline, every windswept dune and rocky tidal flat collectively contains an estimated 7.5 times 10 to the 18th grains of sand. 10 septillion stars exceeds that total by roughly 1,000,000 times. For every single grain of sand on every beach and desert on the entire surface of this planet, there are approximately 1,000,000 stars burning somewhere in the observable universe right now. That number is the backdrop against which the question of life becomes nearly vertiginous. Current data from exoplanet surveys suggests that roughly 1 in 5 stars similar to our own hosts an approximately Earth-sized planet in a zone where liquid water could exist on the surface. Even applying a far more conservative estimate, 1 potentially habitable world per 5 stars across the entire observable universe, the total approaches 2 times 10 to the 23rd candidate worlds. That is 20 trillion planets where the chemistry of life might in principle have gained a foothold. Every smear in the cosmos web mosaic is a galaxy, the barely resolved blobs near the detection limit, the faint, curved arcs stretched by gravitational lensing, the compact, bright points. Each one contains hundreds of billions of the stars in that count. Each of those stars may harbor worlds circling in silence, each world with its own geology, chemistry, and unrecorded history extending across billions of years. The Cosmos Web image covers a patch of sky 3 times the width of the full moon. It represents roughly 100,000th of the total sky. It is a keyhole. Through that keyhole, we have cataloged nearly 800,000 galaxies. If the rest of the sky holds comparable density, the total visible galaxy count across the full celestial sphere approaches 2 trillion. The image is not a photograph of space. It is a photograph of scale. And what that scale discloses, once you examine how those 2 trillion galaxies are arranged across space, turns out to be something even more surprising than the numbers themselves. Gravity does not scatter mass randomly across the universe. It organizes. Given sufficient time, even a marginally denser region of space pulls nearby material inward, grows denser, pulls more strongly, accumulates more mass, until a galaxy forms, then a group, then a cluster, then a supercluster, woven into a web of interlocking structures spanning distances so vast that light takes hundreds of millions of years to traverse them. This process operates simultaneously at every scale, from the smallest galactic halo to the largest continuous structure the observable universe contains. The result has a name: the cosmic web. Dense nodes concentrate thousands of galaxies into gravitational cities where matter has been pooling since the first billion years after the Big Bang. Connecting those cities, elongated filaments of moderate density carry currents of galaxies between clusters, flowing along invisible channels carved by the underlying dark matter architecture. Surrounding the filaments, enormous voids span hundreds of millions of light years in every direction. Regions so drained of matter that galaxies are almost entirely absent. Vast hollow chambers in the fabric of the cosmos. Emily Linder of the Illinois Institute of Technology described the conceptual adjustment this architecture demands. If you knew nothing about the structure of the universe, she said, you might assume galaxies were distributed at random. Stand outside on a clear night, and the stars overhead appear scattered without obvious pattern. Scale that intuition up to the full 3-dimensional cosmos, and you would be profoundly mistaken. Galaxies trace the cosmic web. They concentrate where the dark matter web is dense and avoid the regions where it is sparse. This understanding is surprisingly recent. Before the 1980s, many astronomers assumed that while galaxies clustered locally, They were distributed roughly uniformly at larger scales. Then, the first systematic galaxy redshift surveys mapped thousands of galaxies in 3 dimensions and revealed something nobody had anticipated. Walls of galaxies hundreds of millions of light-years long. Great voids with almost nothing inside. A foam-like structure that looked in cross-section like a soap bubble on a cosmic scale. Webb's contribution is to extend that architecture backward in time. The dark matter map from January 2026 traces the cosmic web to when the universe was approximately 3 billion years old. It shows that the web was already established then, already funneling galaxies into clusters and filaments, already carving voids into the expanding fabric of space. The structures visible in the present-day universe are the mature descendants of what Webb photographs at extreme distance. The cosmic vine, a galaxy filament captured 2 billion years after the Big Bang, is already on its way to becoming a cluster as massive as any we know today. The protocluster JD1, caught in the act of formation 1 billion years after the Big Bang, is a future city of galaxies being observed across 12.5 billion years of its own past. We are inside this web. Our galaxy, our entire local group, occupies a node on a filament connected to larger structures stretching across hundreds of millions of light years. The universe is not a collection of isolated objects. It is a single continuous architecture 13.8 billion years in the making, and Webb has given us the first clear image of its skeleton. What inhabits those bones is something the telescope was never designed to answer, but the question has never felt more urgent. Think about what it means to observe something far away. The instant you see a distant object, the light reaching your eyes left that place some time ago. This is one of the most profound facts in all of science, and James Webb has converted it into the most powerful archaeological instrument humanity has ever assembled. Light travels at roughly 186,000 miles per second. That sounds impossibly fast until you begin measuring it against the scale of the universe. When you look at the moon on a clear night, you see it as it appeared about 1.3 seconds earlier. A small delay, almost imperceptible. But stretch that distance and the delay becomes something staggering. The nearest star beyond our own, a red dwarf called Proxima Centauri, lies 4.2 light-years away. The light from it that reaches Earth tonight completed a 4-year crossing of near-perfect emptiness to get here. During those 4 years, entire political cycles ran their course. Scientific discoveries were made and debated. Children who did not yet exist when that light departed learned to speak. That star had no knowledge of any of it. It simply continued burning. Go farther. The Andromeda Galaxy hangs in the northern sky as a faint smear visible to the naked eye on a clear night. The light that falls on your retina from it tonight departed its source 2.5 million years ago. At that moment, our ancestors were chipping stones into tools on the African savanna. They had no conception of galaxies, telescopes, or the void surrounding them. That ancient light has been crossing space ever since. It did not wait for us to exist. It simply arrived. Now move to a scale that makes Andromeda feel nearby. The galaxy MOM-Z14, confirmed spectroscopically in May 2025 at the highest redshift ever measured, is so distant that its light traveled for 13.5 billion years before James Webb intercepted it. When the telescope converted that signal into an image, it was recording a galaxy as it appeared when the universe was only 280 million years old. Our solar system did not yet exist. the atoms in every human body had not yet been forged inside any stellar furnace. The Milky Way itself was still assembling its earliest structures in the dark. The word telescope has taken on a larger meaning than it once carried. Every image James Webb captures is an archaeological excavation through layered time, each stratum more ancient than the last. The Cosmos Webb survey that cataloged 800,000 galaxies in a single mosaic was not merely counting objects. It was sampling cosmic history at every depth simultaneously. The way a core drilled through ancient ice preserves records of thousands of winters stacked upon one another. Every galaxy in that mosaic is the past itself, arriving here encoded in photons. The scientists studying this data are reading a record unlike anything humans have ever built. Every object in a James Webb image is a dispatch sent across billions of years by something that no longer looks the way it appears. The galaxies have aged. Stars inside them have detonated. New generations have risen. Entire worlds may have formed and ended in the vast interval between when that light departed and when it finally arrived. What you see in every deep field image is a ghost, an extraordinarily precise, scientifically measurable ghost. And the part that deserves a long pause is this. Humanity just built the instrument capable of reading those ghosts with genuine clarity for the very first time. But knowing the instrument exists is only the beginning. The scale of what it is measuring is where the story becomes almost too vast to hold. When humans first invented writing roughly 5,000 years ago, the photon that would eventually reach James Webb and become an image of MOEM-Z14 had already been traveling for 13,495 million years. It had completed 99.996% of its journey. Ancient Sumerians were pressing symbols into clay tablets in Mesopotamia while that photon made its final crossing, oblivious to everything that would one day stand at the end of its path. Go back further. Our solar system coalesced from a spinning cloud of gas and dust approximately 4.6 billion years ago. At that precise moment, the light from MOEM-Z14 still had 8.9 billion more years of travel ahead of it. Our star had not yet ignited. Earth had not yet formed. The first oceans did not exist, and that photon was less than halfway through its crossing, flying through an expanding cosmos in perfect silence. This is the kind of number that refuses to feel real no matter how often you confront it. Consider the photon's journey as a biography. It originated in a compact galaxy roughly 500 light-years across, blazing with star formation in the infant universe. It escaped its home galaxy into intergalactic space and began billions of years of traversing voids so vast and so empty that the probability of encountering any particle along the way was vanishingly small. While it flew, generations of stars rose and died inside the Milky Way. While it flew, the great extinction events of Earth reshaped life on this planet. While it flew, mammals diversified, and one species among them constructed language, philosophy, and science. Then, at a particular moment in deep space, a telescope intercepted it. James Webb's mirror, hexagonal and golden, maintained at 270 degrees below 0 Fahrenheit, gathered that photon together with trillions of others from the same distant source. The telescope's detectors registered its arrival. Software converted the signal into data. Scientists on Earth opened the files and found a galaxy at the boundary of observable time. That photon had witnessed the entire history of Earth from a distance. It did not participate. It simply traveled, carrying information that no human instrument had any way to receive until now. This is why researchers have described James Webb in words that feel almost too large for scientific equipment. Peter Van Dockum of Yale University. When his team confirmed MOM-Z14, observed that sharks have existed on Earth for longer than the age of that galaxy at the moment its light departed. He was reaching for any anchor in human experience that could make the scale feel real. Very few attempts succeed. Every deep field observation plays out the same story at different depths. Some photons in a single James Webb exposure departed when the universe was 300 million years old. Others left when it was 2 billion or 5 billion or 10 billion years old, all arriving simultaneously, all decoded at once. The mosaic this produces is a history of the cosmos from its youth to its present, compressed into a single image. And within that history, something is concealed that no one fully expected to find in such abundance. Stand outside on a clear night and look upward. The darkness between the stars is full of galaxies, most of them invisible to human eyes, all of them receding from one another on a tide of expanding space. The question of how large the observable universe actually is, and what its size truly implies, sits at the center of modern cosmology. The observable universe is approximately 93 billion light-years across. This number puzzles people immediately. If the universe is 13.8 billion years old, and light travels at a fixed speed, how can we see anything 93 billion light-years away? The answer is that space itself has been expanding throughout. An object 13.8 billion light-years away at the moment it emitted the light we now receive has since been carried by that expansion to a position roughly 46 billion light-years from us today. We see its ancient light, but the object is now far beyond that distance. This is not motion through space. Space itself is stretching. The volume enclosed by the observable universe is staggering, roughly 4.4 times 10 to the 80th power cubic meters, a 4 followed by 80 zeros. Inside this volume resides the structure astronomers have spent a century trying to chart. Galaxy clusters, filaments connecting them, enormous voids where almost nothing exists. But here is the detail that quietly changes everything. The observable universe is a sphere defined purely by the speed of light and the age of time. It is a horizon, not a wall. It is precisely like the horizon you see when standing on a beach. The ocean continues past it. You simply cannot see that far from where you stand. There is no scientific reason to suppose the universe ends at the limits of what we can observe. Strong theoretical grounds suggest it extends vastly, perhaps infinitely, beyond regions of space from which light simply has not had time to reach us, or regions so remote that the expansion of space carries them beyond our reach permanently. So their light will never arrive regardless of how long we wait. The Cosmos Webb survey covered roughly 1/1000% of the total sky. Within that narrow window, 800,000 galaxies. Extrapolating to 2 trillion across the full observable universe is already a number that taxes comprehension. But the observable universe is itself only the visible portion of something that may have no boundary at all. Every cosmological model James Webb is testing, every distance record it breaks, every early galaxy it detects in the first few 100 million years after the Big Bang, applies only to the portion of reality we can, in principle, observe. Whatever lies beyond the cosmic horizon is by definition beyond our reach, our knowledge, and our instruments. We are cartographers who have mapped one small district of a city that may extend without limit in every direction. The structures visible to us are extraordinary on their own terms, and those structures, it turns out, are built from something we cannot directly see at all. Most of the universe is invisible. This is a confirmed scientific result, and it is one of the strangest things humanity has ever been required to absorb. Everything detectable by any instrument ever built, every star, every galaxy, every glowing gas cloud, every drifting comet, adds up to roughly 5% of the total energy content of the universe. Dark matter accounts for about 27%, invisible to every form of radiation, but detectable through its gravitational influence on visible matter. Dark energy accounts for roughly 68%, a property of space itself that drives the universe's accelerating expansion. Even within that visible 5%, the emptiness is nearly absolute. The average density of matter in the universe works out to roughly 6 protons per cubic meter. A cubic meter is the size of a large cardboard box. Fill that box with ordinary air, and it contains around 25 trillion molecules. Fill it with the average matter content of the cosmos, and you get 6 protons. The universe, for all its galaxies and stars and visible complexity, is more than 99.999999% empty space. And yet it does not look empty. The cosmos web mosaic is filled with light. The dark matter map published in January 2026 is dense with structure. How can something be simultaneously that vacant and that richly organized? The answer is clustering. Matter follows the invisible architecture of dark matter filaments, collapsing into dense knots of galaxies while leaving behind enormous voids that span hundreds of millions of light years. Those voids are genuine abysses, regions of the cosmos, where you could travel for 100 million years and encounter almost nothing. The bright galaxies in every deep field image are the extreme concentrations, the mountain peaks of a landscape that is otherwise flat and barren. There is another dimension to this emptiness that touches something quietly unsettling. 2 trillion galaxies should, by naive calculation, make the night sky blaze with uniform light. Every line of sight should eventually intersect some distant galaxy. The sky should not be dark. This puzzle, first formally stated by the German astronomer Heinrich Wilhelm Olbers in the 19th century, persisted for generations. The resolution is the expansion of space itself. As the universe expands, light from distant galaxies is stretched to wavelengths too long for human eyes to detect, shifted into infrared and microwave ranges invisible without instruments designed for them. The galaxies are there. Their light is there. We simply cannot perceive it without machines built specifically to receive it. James Webb was built for exactly those wavelengths. It has uncovered more of what was hidden in the dark than any instrument before it. And what it has uncovered is now raising a question that reaches far beyond the borders of astronomy. Here is a number worth sitting with for a moment. 200 million. That is a conservative scientific estimate for the number of technological civilizations that might exist or have existed in the observable universe, derived from calculations drawing on galaxy counts, stellar populations, and what we understand about the fraction of stars hosting planets under habitable conditions. 200 million civilizations, each separated from the others by distances so vast that a signal traveling at the speed of light between galaxies would require millions of years just to cross the gap. and humanity has detected not one signal from any of them. Every galaxy James Webb reveals is a candidate. The Cosmos Webb mosaic contains 800,000 galaxies, each typically harboring hundreds of billions of stars, many of those stars hosting planets. Every faint smear of light in that image represents a system of worlds as old as or older than our own, built from the same physics, the same chemistry, the same raw materials that produced life here. The James Webb deep fields have sharpened what was already one of the most disquieting problems in science. The Italian physicist Enrico Fermi posed it in a single sentence during a lunch conversation in 1950. If intelligent life is so probable across a universe this vast, where is everybody? The question was nearly casual at the time. Decades of accumulating evidence have transformed it into a genuine scientific mystery, with implications reaching from biology to philosophy to long-range human planning. Every new galaxy James Webb identifies deepens the silence. Each one is another data point in a distribution that keeps converging on the same result. The universe is vast. It has been hospitable to life for billions of years, and nothing has announced itself. There are those who find this silence reassuring. If no civilization in 13 billion years has achieved interstellar reach, perhaps the obstacles to doing so are steeper than we assume. Perhaps no one is coming. Others find the silence the most troubling fact in science. It has outlasted every improvement in telescope capability. It survived the discovery of exoplanets by the thousands. It survived the confirmation of complex organic chemistry in environments once thought sterile. The silence is durable, and each new image from James Webb makes it louder by contrast. Every blank square of sky in a deep field contains galaxies too faint to resolve, stars too distant to study, worlds too remote to examine, and none of them have transmitted a signal that any human instrument has ever received. They are, as far as all evidence shows, simply there, burning, aging, silent. The question of why leads to answers that offer no easy comfort. The silence demands explanation, and scientists have offered several. None of them are comfortable to inhabit. The first possibility carries a name researchers call the Great Filter. The concept holds that somewhere along the path from simple chemistry to an interstellar civilization lies a barrier so formidable that almost no species crosses it. The question with real weight is where that filter lies. If it sits behind us, somewhere in the emergence of complex cellular life, the development of multicellular organisms, or the rise of sustained intelligence, then we are extraordinarily rare. The silence is explained by the fact that we are among the very first to have made it through. That possibility, strange as it sounds, is flattering. It makes Earth near miraculous and human civilization genuinely precious in a universe that has been attempting and failing to produce complexity for billions of years. If the filter lies ahead, the implications invert completely. It would mean civilizations consistently reach a certain threshold of technological capability, and then collapse before spreading beyond their home star system. Our current moment, with its accumulating technological risks and global pressures, would look less like a difficult passage, and more like the place where the chain reliably breaks. The second framework concerns distance and time, rather than biological rarity. The observable universe is 93 billion light-years across. A civilization in a galaxy 50 million light-years away that began transmitting signals would need to aim precisely at our location, generate signals powerful enough to survive the crossing, and hope we were listening in the right direction at the right moment. Communication between galaxies at light speed takes millions of years. Human civilization has existed for roughly 10,000. The timing problem alone could account for the silence without requiring that life is uncommon. A third possibility that researchers increasingly consider plausible is that we are early. The universe at 13.8 billion years old is young by its own measure. It will remain capable of sustaining stellar systems for hundreds of billions of years more. Complex life may only now be beginning to emerge at meaningful scale. We may be among the first rather than a latecomer. Each of these answers carries different implications for how humanity's future should be approached. James Webb cannot determine which one is true, but every image it captures makes the question feel more urgent and less abstract. Before wonder solidifies into certainty, it is worth pausing for honest doubt. Science advances through challenge, and cosmology is no exception. The 2 trillion galaxy estimate is a projection, not a direct tally. Christopher Consolis and his colleagues at the University of Nottingham built that figure through 3-dimensional modeling of galaxy density across cosmic time, accounting for galaxies too faint and distant for current telescopes to detect directly. The model is sophisticated and well regarded, but it remains a model. The actual number could be higher. It could be somewhat lower if assumptions about faint galaxy formation require revision. The impossible galaxies problem is real. The gap between what the standard cosmological model predicted and what James Webb found at extreme redshifts is too large to dismiss. Yet most working cosmologists are not prepared to declare the underlying framework broken. The leading interpretation is that the early universe produced stars more rapidly than models assumed, possibly because the feedback mechanisms that ordinarily suppress star formation were less effective in those first few 100 million years. This demands significant revision to our models, but may preserve the core structure. Some early distance records from the telescope's first years were revised downward after careful spectroscopic follow-up. Objects that appeared extraordinarily distant in photometric data turned out, when measured precisely, to lie at lower redshifts. The field has learned caution, and the most recent confirmed records come with thorough spectroscopic verification. The most important caveat concerns life. Our sample size is 1. We know life exists on Earth. We know of no confirmed life anywhere else. Drawing statistical conclusions about the probability of life across 2 trillion galaxies from a sample of 1 is as much motivated reasoning as genuine inference. The honest scientific position is neither that life is everywhere nor that we are alone. It is that we simply do not yet know, and the tools capable of beginning to find out are only now becoming available. Euclid, launched in 2023, is mapping large-scale structure at scales Webb cannot reach. The Nancy Grace Roman Space Telescope will survey areas far exceeding Webb's deepest fields. Ground-based observatories coming online this decade will make atmospheric spectroscopy of distant planets routine. That means we are also at the opening of an era of revision. What we know now is real. What we believe it means is provisional. Holding both truths at once is not weakness. It is science practiced at its best. Carl Sagan wrote in the 1970s that if it is just us in the universe, it seems like an awful waste of space. He was trying to convey a feeling that resists precise quantification, the sense that the scale of the cosmos implies something about its possibilities. He could not have known that half a century later, a telescope in deep space would produce the most detailed inventory of that space ever assembled. And he could not have known how completely the images would deepen rather than resolve the feeling he was describing. The James Webb images do something to people. They are measurements. The Cosmos Webb mosaic is a scientific catalog, processed through infrared detectors and color-mapped to wavelengths human eyes can interpret. But at its foundation it is a record of actual light from actual galaxies that genuinely exist. Billions of them, each containing hundreds of billions of stars. And when you understand what you are looking at, the weight of it settles in slowly. 1 galaxy out of 2 trillion. That is our address. The Milky Way, a moderately large spiral roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. 1 of 2 trillion. Within it, one unremarkable star among those hundreds of billions. Around that star, one planet at the right distance with the right chemistry, generating life that eventually looked upward and asked what else was out there. The dark matter map, published in January 2026, disclosed something that sits quietly at the center of all of this. The universe is organized, structured along invisible filaments spanning billions of light years, clusters of galaxies threaded together by channels of lower density, surrounded by voids stretching for hundreds of millions of light years. The architecture is hierarchical, intricate, and consistent across the entire observable universe. A cosmos this organized does not look like an accident. Whether that observation carries deeper meaning is a question science cannot yet answer, and may never be positioned to answer definitively. But the fact of the organization, the sheer improbability of a universe, simultaneously this vast and this precisely structured, carries a quality that the word coincidence struggles to contain. James Webb was built because a species on one planet, orbiting one ordinary star in one of 2 trillion galaxies, decided that comprehending the universe was worth $10 billion and decades of collective human effort. That choice says something about consciousness that has no known equivalent anywhere else in the cosmos we can observe. And what consciousness has found, looking back across 13.8 billion years of cosmic history, is that the more clearly we see, the larger and more luminous the mystery becomes. There is a moment described by Diana Scognamiglio of NASA's Jet Propulsion Laboratory that captures something essential about working at the frontier of knowledge. In May 2025, she displayed a comparison slide at a scientific collaboration meeting, placing the new James Webb dark matter map alongside the finest previous map of the same region. The room went quiet. Then people began applauding. She called it recognition, not courtesy. A room full of scientists beholding the shape of an old question resolved with new precision. That moment is a small aperture into the story this documentary has been assembling across 30 chapters. James Webb was not built merely to generate beautiful images. It was built to confront questions that had been piling up for a century. How did the first galaxies form? How did the cosmic web crystallize from the smooth plasma of the early universe? What transpired in the first few 100 million years after the Big Bang? How common is the chemistry that gives rise to complex molecules? The telescope has offered partial answers to all of these, and in doing so has generated more new questions than it has laid to rest. That is precisely how science moves forward. The galaxy MOM-Z14, 13.5 billion light-years away, blazed with star formation before the Milky Way had taken shape. The protocluster JD1, actively assembling 12.7 billion light-years away, demonstrated that the largest structures in the universe were constructing themselves a billion years earlier than models had predicted. The Cosmos Web Survey revealed 800,000 galaxies in a patch of sky 3 times the width of the full moon, and that patch is 1,000th of 1% of the total sky. The dark matter map made the invisible scaffolding of the cosmos visible with genuine resolution for the first time. Each of these is an opening, a door left ajar. The observable universe spans 93 billion light-years. It contains 2 trillion galaxies and roughly 10 septillion stars. More stars than there are grains of sand on every beach and desert on the surface of this planet combined. At a conservative rate of 1 Earth-sized world per 5 stars, the number of potentially habitable worlds in the observable universe extends into the hundreds of millions of trillions. And we are here, on one of them, using instruments built from materials forged in the cores of dead stars, launched on rockets designed by engineers and mathematicians, operated by scientists who gave careers to assembling one clear picture of what exists, looking back at all of it, trying to understand what it means. James Webb gathers light that has been traveling since before Earth existed and converts it into knowledge. It observes galaxy clusters in the act of being born. It detects oxygen in galaxies that formed when the universe was barely 2% of its current age. It charts the invisible architecture of dark matter across billions of light-years. Every image it transmits is a fact about a universe that had no obligation to be comprehensible. And yet here it is, partial, imperfect, provisional, and genuinely comprehensible. The same laws that governed the formation of MOM-Z14 govern the computer processing its data, the mind interpreting that data, and the planet turning quietly beneath them all. That connection between a galaxy 13.5 billion light-years away and a species young enough to still be surprised by what it finds is the most astonishing thing the telescope has ever captured. We are not standing outside the universe, observing something alien. We are the universe, looking back at itself. And in that act of looking, something remarkable is happening. A cosmos that existed for billions of years in silence, without witness, without record, is being seen for the first time. The light that traveled those immense distances, across all those eons of expanding space, did not arrive for nothing. It arrived for this, to be caught by a golden mirror in the deep cold of space, converted into data, and read by a mind that emerged from the very same physical laws that shaped the stars that sent it. The universe did not need us to exist. And yet here we are, small and brief and improbably aware, standing at the edge of everything detectable, asking what lies beyond. That question may be the most human thing there is. And James Webb, instrument of gold and silicon and collective ambition, exists to make sure we keep asking it with ever greater clarity and ever greater wonder, for as long as we have the courage to look.